Imagine a star so powerful that if it passed halfway between the Earth and the Moon, it would wipe every credit card on our planet clean in less than a second. A star that can twist the very structure of atoms, distort space itself, and unleash bursts of energy that briefly outshine entire galaxies. This is not science fiction. This is the reality of one of the most extreme objects in the universe, the magnetar. In the vast silence of space, where most stars quietly burn for billions of years, magnetars are different. They are violent, unstable, and almost impossibly intense. They represent a limit, perhaps the limit of how extreme matter and energy can become. But how does something like a magnetar even form? And what happens when one awakens? To understand magnetars, we must begin with something more familiar: a star. Not just any star, but a massive one, many times larger than our sun. For millions of years, it lives a relatively stable life, fusing hydrogen into helium, shining steadily into the darkness. But like all stars, it carries within it the seeds of its own destruction. Eventually, the fuel in its core begins to run out. Gravity, which has been held back for so long by the outward pressure of nuclear fusion, begins to win. The core collapses inward in a fraction of a second, triggering one of the most powerful explosions in the universe, a supernova. In that moment, the outer layers of the star are blasted into space, while the core is crushed into something entirely new. If the star is massive enough, it might collapse into a black hole. But if it falls within a certain range, something else is born: a neutron star. A neutron star is already an object of extremes. Imagine compressing the mass of our sun into a sphere just about 20 kilometers across. The density becomes so immense that atoms themselves collapse. Electrons and protons merge into neutrons, creating a giant atomic nucleus floating in space. But among neutron stars, there exists a rare and even more extreme subclass. These are magnetars. What makes a magnetar different is its magnetic field. Not just strong, but unimaginably strong. Trillions of times stronger than Earth's magnetic field. Billions of times stronger than anything we can produce in laboratories. It is the most powerful magnetic force known in the universe. To put this into perspective, if a magnetar were as far away as the Moon, its magnetic field could still disrupt electronic devices on Earth. But up close, the effects are far more bizarre. The magnetic field is so intense that it can distort the shapes of atoms themselves, stretching them into long, thin structures. Chemistry, as we know it, would cease to exist. Even light is affected. In the presence of such a powerful magnetic field, empty space behaves differently. Photons can split, merge, and interact in ways that defy our everyday understanding. The vacuum itself becomes a kind of medium, altered by the magnetar's presence. But where does this incredible magnetism come from? Scientists believe it is born during the chaotic moment of the neutron star's creation. As the core collapses, it begins to spin faster and faster, like a figure skater pulling in their arms. At the same time, convection and turbulence inside the newborn neutron star generate a dynamo effect, amplifying the magnetic field to extraordinary levels. The result is a magnetar, spinning, ultra-dense object wrapped in a magnetic field so powerful it can literally crack its own surface. Yes, crack. The crust of a magnetar, though incredibly strong, is constantly under stress from the shifting magnetic field beneath it. Eventually, the strain becomes too much, and the crust fractures in what scientists call a starquake. When this happens, the energy released is staggering. In a fraction of a second, a magnetar can release more energy than our sun emits in 100,000 years. These events are observed as gamma-ray bursts or soft gamma repeaters, some of the most energetic phenomena ever detected. One such event, detected in 2004, came from a magnetar located about 50,000 light-years away. Despite the immense distance, the burst was so powerful that it briefly altered Earth's upper atmosphere. Satellites were overwhelmed. Instruments designed to observe distant cosmic events were saturated almost instantly. And this raises an unsettling question: what if the magnetar like that were closer? Fortunately, there are no known magnetars dangerously near Earth. The closest known ones are thousands of light-years away. But in cosmic terms, distances can be deceiving. The universe is vast, but it is also dynamic, constantly changing. Magnetars are not stable objects. Unlike many stars that live for billions of years, magnetars have relatively short lifespans. Their intense magnetic fields gradually decay over tens of thousands of years, a blink of an eye in cosmic time. As they lose energy, they may transition into more typical neutron stars, fading into obscurity. But during their active phase, they are among the most fascinating objects in the universe. They emit powerful beams of X-rays and gamma rays, often in irregular bursts. Some magnetars rotate rapidly, sweeping their radiation across space like cosmic lighthouses. Others are slower, their emissions more chaotic, more unpredictable. And recently, magnetars had become even more intriguing. In 2020, astronomers detected a mysterious signal known as a fast radio burst, or FRB, coming from within our own galaxy. For years, FRBs had been one of the biggest mysteries in astrophysics. Brief, intense flashes of radio waves lasting only milliseconds, originating from distant galaxies. But this time, the signal was close, and it was traced back to a magnetar. This discovery provided the first direct evidence linking magnetars to fast radio bursts. It suggested that at least some of these enigmatic signals, once thought to potentially come from exotic phenomena like merging black holes or even hypothetical alien technologies, could be explained by magnetar activity. But how exactly do magnetars produce these bursts? The answer is still being explored. Some theories suggest that starquakes can trigger sudden rearrangements of the magnetic field, releasing energy in the form of radio waves. Others propose that interactions between the magnetar's magnetic field and surrounding plasma create the conditions necessary for these bursts. Whatever the mechanism, the implications are profound. It means that magnetars are not just powerful, they are also key to understanding some of the universe's most mysterious signals. And yet, for all we have learned, magnetars remain deeply enigmatic. What lies beneath their crust? How exactly does matter behave under such extreme conditions? Could there be even more exotic objects beyond magnetars, pushing the limits even further? As we peer deeper into the cosmos, detecting signals from across billions of light years, we are constantly reminded of how little we truly understand. The universe is not just stranger than we imagine, it is stranger than we can imagine. And magnetars are a perfect example of that strangeness. They are remnants of destruction, born from the death of massive stars, yet capable of influencing space across unimaginable distances. They challenge our understanding of physics, forcing us to rethink what is possible. But perhaps the most fascinating thing about magnetars is not just their power, but what they reveal about the universe itself. Because in studying these extreme objects, we are not just learning about distant stars. We are uncovering the fundamental laws that govern reality, laws that apply not only in the far reaches of space, but here, on Earth. And so the question remains, what else is out there, waiting to be discovered? What other cosmic phenomena are hiding in the darkness, sending signals we have yet to decode? And could magnetars be just one piece of a much larger puzzle? The deeper we look, the more mysteries we find, and each answer only leads to more questions. Because in the end, the universe is not just a place of answers, it is a place of endless wonder. For a long time, magnetars were thought to be rare, almost exotic exceptions in the cosmic landscape. Only a handful had been identified, scattered across our galaxy like hidden landmines of extreme physics. But as our instruments have grown more sensitive, as our telescopes have expanded beyond visible light into X-rays, gamma rays, and radio waves, something unexpected has begun to emerge. The universe may be far more populated with these magnetic titans than we once believed. Every time a new magnetar is discovered, it brings with it a new puzzle. Some behave as expected, emitting periodic bursts of radiation, slowly spinning down as their immense magnetic fields lose energy. But others defy prediction. Some suddenly awaken after years of silence, releasing violent flares without warning. Others exhibit strange timing irregularities, as if their internal structure is shifting in ways we do not yet fully understand. It is as though magnetars are not just objects but processes. Dynamic, evolving systems that continue to surprise us. And then there is their surface, a place unlike anything else in the universe. The crust of a magnetar is often described as solid, but that word barely captures its nature. It is believed to be composed of a lattice of atomic nuclei packed so tightly that a single teaspoon of this material would weigh billions of tons. Yet even this unimaginable density is only the outer layer. Beneath it lies a sea of neutrons, possibly mixed with exotic particles that we have never directly observed. Some theories suggest the presence of nuclear pasta structures with bizarre shapes like sheets, tubes, and spirals, formed under the immense pressure and gravity. Others propose that even stranger states of matter might exist, where quarks themselves begin to move freely. Could there be a phase of matter inside magnetars that we have never recreated on Earth? And if so, what does that say about the limits of physics? The magnetic field complicates everything further. It doesn't just sit outside the star, it penetrates deep into its interior, influencing how matter behaves at every level. It can suppress certain particle interactions while enhancing others, creating conditions that challenge even the most advanced theoretical models. Trying to simulate a magnetar on Earth is, in many ways, impossible. Our most powerful particle accelerators, like those operated by organizations such as CERN, can recreate some aspects of high-energy physics, but they cannot replicate the combination of gravity, density, and magnetism found in these stars. So instead, scientists rely on observation. Orbiting telescopes like Chandra X-ray Observatory and XMM Newton scan the skies, capturing bursts of high-energy radiation from distant magnetars. Each flare, each pulse, carries information encoded clues about what is happening inside these extreme objects. And sometimes, those clues arrive in unexpected ways. In recent years, astronomers have detected magnetars behaving in ways that blur the lines between known categories of cosmic objects. Some magnetars have been observed emitting radio pulses similar to those of pulsars, another type of neutron star. Others have shown signs of interacting with surrounding material, creating nebulae powered not just by rotation, but by magnetic energy itself. It raises an intriguing possibility. Are magnetars and pulsars part of a continuum, rather than entirely separate classes? If so, then perhaps many neutron stars go through a magnetar phase at some point in their evolution. Perhaps what we are seeing is not a rare anomaly, but a stage, a brief, violent chapter in the life of certain stars. But magnetars are not only important for understanding stellar evolution. They may also hold the key to answering one of the biggest questions in modern astrophysics. What powers the most energetic events in the universe? Consider gamma-ray bursts. These brief flashes of gamma radiation can release more energy in a few seconds than the sun will emit over its entire lifetime. For decades, their origins were shrouded in mystery. Some were eventually linked to collapsing stars or merging neutron stars, but not all. Could magnetars be responsible for at least some of these bursts? There is growing evidence that they are. When a magnetar undergoes a catastrophic reconfiguration of its magnetic field, a process sometimes referred to as magnetic reconnection, it can release an enormous amount of energy almost instantaneously. This energy can escape as gamma rays, traveling across the universe and reaching our detectors as a sudden, intense flash. But even this might not be the full story. Some scientists have proposed that newly formed magnetars, spinning at incredible speeds, could act as central engines for certain types of gamma-ray bursts. In this scenario, the magnetar's rotational energy is converted into radiation, powering a sustained emission that can last for minutes or even hours. If true, it would mean that magnetars are not just isolated phenomena but central players in some of the most dramatic events in the cosmos. And yet, despite all this, there is still so much we do not know. For example, what determines whether a collapsing star becomes a black hole or a magnetar? Is it purely a matter of mass, or do other factors like rotation speed or magnetic field strength during collapse play a role? And what about the upper limit of magnetic strength? Magnetars already push the boundaries of what physics allows. But could there be objects with even stronger fields? Could there be hypermagnetars or entirely new classes of stars that we have yet to discover? These questions are not just theoretical. They have real implications for how we understand the universe. Because magnetars do something very important, they test the limits. They exist at the edge of what is physically possible, where our equations begin to break down, where small uncertainties can lead to vastly different predictions. By studying them, we are effectively stress testing our understanding of reality itself. And sometimes, those tests reveal cracks. Take, for example, the behavior of light in extreme magnetic fields. Under normal conditions, light travels in straight lines, unaffected by other light. But near a magnetar, the rules change. Quantum electrodynamics predicts that the vacuum becomes birefringent, meaning that light can split into different polarization states, traveling at slightly different speeds. This effect has been observed, confirming predictions made decades earlier. It is a reminder that even empty space is not truly empty. It is a dynamic medium, shaped by the forces acting upon it. And magnetars, with their overwhelming magnetic fields, are among the few places in the universe where we can observe such effects directly. But perhaps the most haunting aspect of magnetars is their unpredictability. Unlike many astronomical objects that follow relatively stable patterns, magnetars can remain quiet for years, even decades, and then suddenly erupt in a burst of energy that defies expectation. There is no reliable way to predict when this will happen. It is as if they are ticking time bombs scattered throughout the galaxy, silent, invisible, waiting. What would it look like if one went off nearby? Not close enough to destroy Earth outright, but close enough to be felt. The answer is both fascinating and unsettling. A powerful magnetar flare could flood our planet with high-energy radiation, potentially damaging satellites, disrupting communications, and even affecting the atmosphere. It would not necessarily be an extinction-level event, but it could have significant technological consequences. In a world increasingly dependent on electronics, such an event would not go unnoticed. And yet, we would likely have no warning. Because even though we have mapped thousands of stars, the galaxy is vast beyond comprehension. There may be magnetars hidden behind clouds of gas and dust, their emissions too faint or too infrequent to detect until it is too late. This is the paradox of modern astronomy. We have never known more about the universe than we do now. And yet, the more we learn, the more we realize how much remains hidden. Magnetars are a perfect embodiment of this paradox. They are both known and unknown, understood and mysterious. They challenge us, inspire us, and occasionally frighten us. But above all, they remind us of something fundamental. The universe is not a gentle place. It is a realm of extremes, where forces beyond our everyday experience shape reality in ways that are both beautiful and terrifying. And somewhere out there, in the dark between the stars, magnetars continue to spin, to crack, to erupt, sending their signals across the cosmos. Signals that we are only just beginning to understand. Signals that may carry answers to questions we have not yet thought to ask. So the next time you look up at the night sky, consider this: among those distant points of light, there may be objects so powerful that they defy imagination. Objects that could reshape our understanding of physics, of matter, of space itself. And perhaps one day, we will uncover all their secrets. Or perhaps they will remain as they are now, mysterious, silent, waiting.